Hello, it's Scott Manley here. After Starship's recent landing in the Indian Ocean, there was much discussion about the awesomeness of this footage, and Elon Musk decided to come on Twitter and say, hey, did you know that we did that with a camera strapped to a Starlink put in a kiddie pool in the middle of the ocean? Well, it is a little more complicated than that, but I thought this would be a perfect moment for us to discuss the history of engineering cameras, the cameras that provide the awesome footage of these rockets as they go through ascent. Now, these are cameras that are designed to help the engineers understand the rocket, understand how things went wrong, and the fact that they produce some cool pictures is frequently a secondary thing, but it's the thing that we really appreciate. But I'm not going to start with SpaceX because, SpaceX is a private company. We have very limited information. Instead, I'm going to go back to the very earliest days of spaceflight. Because, NASA is a public organization and a lot of their hardware is documented in various papers, including the cameras they used. So yeah, it seems that the US was flying engineering cameras on rockets very early in the development. These were usually concerned with observing things like stage separation sequences to ensure things were working correctly. And so we start out with Atlas, which was being developed as a missile, an intercontinental ballistic missile, and there were multiple flights carrying engineering cameras to make sure its staging system worked. There's one example. We have two film cameras which were mounted on external pods, and these were very easy to see because they were painted bright orange on the outside of the rocket. They were sticking out. Now, I'm presuming that these were like 16mm film cameras with a range of speeds, but one camera shot through a window and looked at the Y duct, which is a portion of the plumbing which moved liquid oxygen from the tank to the engines. And the engineers were looking for things like excessive vibration, leaks, or maybe even small fires. They would run at high frame rates, and seconds after liftoff, they would run out of film. Then they would be ejected and recovered near the launch site. Now, the fact that these stuck out the side a whole lot didn't matter so much because they were dropped after only a few seconds in flight before the rocket really picked up a lot of speed. Now, furthermore, on the Atlas, there would be two other cameras which are often seen, which would remain on board to capture the staging sequence, or rather the half-staging sequence, where on the Atlas they dropped the outer booster engines and a section of the aerodynamic fairing, leaving just the sustainer engine to carry it through from the 50-mile altitude up to orbit. So one camera would be sitting on the outside of the rocket looking down, and this would see the stage falling away. The other would be on the interior and looking up, and it would see the stage or the fairing come away around it. And then after observing this sequence, the cameras would then eject themselves, literally falling through the rocket exhaust of that core engine while it was still burning. I mean, they couldn't afford to wait for that engine to shut down because that engine would actually continue to fire all the way into orbit. So the same kind of recoverable camera setup was also used on the Titan II missile. And again, looking at the staging using high frame rate cameras and then ejecting the camera pods so that they can be recovered downrange in the ocean. Now for the Titan II, they were changing a lot of things about the rocket. They were simplifying many parts of the rocket. And one of the things that they thought would simplify it was by removing the staging motors, right? The stage separation system. So instead of separating the rocket and then lighting the engine, they were going to go and do hot staging. As such, engineers were no doubt interested, and one might even say excited to see what happens when you light a rocket engine when it's still inside the interstage of the previous stage. The footage we have shows one flight with an exterior camera and then another with an interior camera, and both show the violent separation process with panels blowing out due to the pressure of the rocket exhaust. So now we move forward to the Apollo program. And since this was a civilian program, we have a lot more information on what happened. For example, we now start to see references in the documentation for specific camera manufacturers and the models that were used. For the high-speed engineering cameras, I specifically found mention of DB Millikan high-speed 16mm film cameras, which were able to shoot at a range of speeds up to like 500 frames per second. And these actually had a fairly long established history in spaceflight. They were introduced in the 1950s, and they were used to shoot engineering footage of like historic NASA launches as early as Alan Shepard's Mercury flight. They were also mounted on Balls 8. That's the famous B-52 which carried a number of X-planes, including the X-15. So when that X-15 drops away, that is a 16mm DB Millikan camera. Millikan would also build the compact 16mm film cameras that were used on board spacecraft, like the Mercury capsule had some 16mm film cameras that were used, either over the shoulder or pointing at the astronaut. So anyway, NASA had a number of film cameras on the second stage of the Saturn V, or the first stage of the Saturn I, to carry the staging events with the upper stage. So about 20 seconds after the stage separation, a small explosive charge would pop these pods out of the rocket and they'd sort of tumble through space for the next few minutes. They would actually initially climb because they were going upwards. And some of them, I think, would reach altitudes of something like 800,000 feet, something ridiculous, 200, 300 kilometers. And then they would fall back. And to survive splashdown in the Atlantic, usually several hundred miles down range, there was a switch which would trigger a power balloon. It wasn't a parachute, it was just a balloon that would inflate, decreasing their terminal velocity sufficiently that they would land in the water and then float. Then they would have like a mini balloon that would go up with an antenna and that would beam a tracking signal, and Navy teams would be out there like battling sharks and stuff to scoop them up. Now, not every pod made it back home safely. Some from early Saturn I tests actually washed ashore weeks later after hurricanes had made recovery impossible. But frequently the film was in still good nick. So this setup ran from like the SA-5 test in 1964 through Apollo 8 in 1968, giving those iconic separation shots. Although the best quality film showing the Saturn upper stage does come from the Saturn 1B rather than the Saturn V, and we usually see that substituted in documentaries. And as rocket nerds, I am sure you all know this, but also because it's such damn good footage compared to the Saturn V, you don't mind being hoodwinked and getting this substituted footage instead. Now, less well known is there cameras on the first stage of the Saturn V, and these really were innovative in pushing the limits of technology at the time. Firstly, they wanted to look inside the liquid oxygen tank during flight, and the ideal position for the viewport would basically be incompatible with the camera existing or being recoverable. So NASA pioneered the use of fiber optic bundles for imaging to basically take the image from the top of the oxygen tank and move it down flexible fiber optics towards where the camera was mounted on the outer ring of the interstage. These were, again, film cameras so that they could be ejected and recovered, and by moving the camera out to the edge, that became possible. Now also, according to a NASA historian, the first two Saturn V launches also included TV cameras in the engine section of the first stage, and they transmitted live imagery of engine startup and operations. And that sounds absolutely awesome, but unfortunately I've not been able to find any evidence of this video. If it's ever been released in any form, it would be really cool to find it. Anyway, one problem was that the cameras and their film needed to be in places that could easily be ejected, as I mentioned, right, with the oxygen thing. And that meant that there was a few things that they wanted to film that they couldn't film because they couldn't get a camera near it. Now, the fiber optics was one option, but another option that NASA investigated was the concept of having a camera in one location and then storing the footage elsewhere in a return pod, in a location that could be ejected. Now, obviously these days you would just run a wire carrying the video data. But in this case, when I said footage, I literally mean hundreds of feet of 16mm film. So they built and tested a system where the film from the camera would move through the shutter and then into a tube, which would run all the way to the pickup reel elsewhere in the rocket. And in fact, they could have multiple pickup reels in a capsule for recovery. They tested this, they verified it. I think it's a really cool thing to mention, but it never flew. While I wanted to talk about the onboard cameras, I also probably should take a quick diversion, a quick side quest to talk about the engineering footage which came from the ground. And that is very much part of that epic Saturn V experience. First off, picture this, it's launch day at Kennedy Space Center. The massive Saturn V is poised on pad 39A, and to document every single fraction of a second that beast lifting off, NASA deployed 106 engineering cameras all around the pad. And these were obviously not like everyday point and shoot things, right? They didn't have iPhones. They were rugged, high-speed film cameras strategically placed to capture the action from every single angle. Some were bolted right into the flame trench. basically, next to the massive flame deflector channeling the exhaust away, and the camera's just like trying to survive. Others were perched on the launch umbilical tower, low and high platforms, various points, and some were like much further out. Like there were a number of sites around the area so that they could actually measure the launch vehicle as it flew and actually, accurately model its trajectory and motion. So how does a camera survive Saturn V engine ignition? I mean, that's no joke, right? The heat and shock waves are, well, insane. So these cameras were hunkered down inside hardened enclosures made basically of like heat shield technology. There was like a steel case, aluminium case, there was ablative paint, they had like thick quartz glass on the outside, there would be shutters that would close over. There are like stories of housings with the cameras getting knocked loose by the blast, but the cameras just kept on running, capturing the footage right up until impact. Like power cables were wrapped in thermal shielding. Everything was wired to the launch control center for remote operation, and operators could like tweak sequences on the fly, monitoring. There was like TV cameras that they could monitor so they could monitor things via closed circuit TV. And they could also track the rocket using like bore sight cameras and things like this. So some of the most iconic imagery, I think, comes from camera E8 on the umbilical tower, and that was 16mm film cranking out at 500 frames per second. So that gave it a super slow motion effect. It turned 30 seconds of high energy chaos into over 8 minutes of mesmerizing detail, showing every single flicker of those F1 engines lighting up and beginning their ascent. So now the ground engineering cameras, they not only shot iconic footage, the technical requirements for this program actually contributed to the Saturn V's iconic looks. All that footage wouldn't mean much without knowing exactly how the rocket was twisting and turning. So the Saturn V had these distinct black and white markings. They weren't just for looks, they were engineering like smarts in paint form. The rocket sported like bold roll patterns, black stripes, rectangles, bands, little cross sections. All of these things were designed to be hard, high contrast things that could be optically tracked by technicians on the ground so that they could back out the exact vehicle motion, not just in ascent, but also in roll and of other rotation, right? This was, something that was important. Not only did they track the motion, but they could actually track flexing of the vehicle with this. It was basically like a barcode. I mean, that's really what it is, right? This rocket has a barcode. So anyway, and so of course this black and white paint pattern actually goes back to the V2, which of course a certain Werner von Braun also worked on. But it wasn't all like fun and games because, for example, they found out that there was a lot of black paint on the interstage of the first stage. And the unfortunate technicians on the ground, the pad rats, they found that that made the interstage uncomfortably hot. And it actually was causing problems with some of the sensors in the interstage. So they actually repainted that particular section to stop it being black to avoid this particular problem. Now, I said that some early versions of the Saturn V had TV cameras, but we do actually have some TV camera engineering footage from the Apollo program. The SA-9 launch, that carried what was called the Pegasus payload, and as it reached orbit, they used TV cameras to observe it unfurling its massive wings. These wings were basically designed to detect meteorites and figure out whether the crew would be safe in orbit for long periods of time. So that was an example of TV cameras actually being used in space. But anyway, for NASA's next launch vehicle, the Space Shuttle, the same camera systems were used. In many cases, the cameras and housings from the Apollo program were adapted and reused for the Shuttle program. There had to be many changes to cover area of interest, which were relevant to the shuttle, and also changes to cover the new pad conditions, because, for example, the Space Shuttle's solid boosters were now wider spaced, and the heating from this was much more intense. I mean, although the shuttle didn't have as much thrust as the Saturn V, the mass flow and heating from these solid boosters actually made it a harder environment for the cameras on the ground. The Space Shuttle's engineering camera system would begin to make more use of television cameras as well and videotapes so that they could collect data on the pad, but there would be plenty of new film cameras introduced for the Space Shuttle because film was still really good. In particular, film had much better behavior when it was exposed to the very, very bright booster exhausts compared to the less bright engine exhausts, the center engines. But in flight, the Space Shuttle did actually carry some engineering cameras from its earliest flights. The external tank had to connect to the orbiter during launch via umbilical plates, which were through the heat shield, and so there's a pair of doors that had to open for this. And behind these doors with the umbilical connectors, there were 16mm motion picture cameras. One had a 5mm lens, the other with a 10mm lens, and they were on the LH2 well on the orbiter's aft underside. There was also a 35mm sequential still camera that was installed on the LOX umbilical well. And so these were positioned to capture views through the open umbilical doors during ascent and separation. So they would actually capture booster separation during launch. And later, when the external tank was separated, this would happen at a much slower, more sedate experience, allowing them to capture many more images of the external tank and the state of it after ascending through the atmosphere. So they could see the blackening of the surface. They could see how it had been damaged. And this was all captured on film, which would then have to be recovered, brought home, developed, so that it wasn't seen until after flight. After the Columbia disaster, these cameras were switched to digital systems that could downlink the imagery while they were still on orbit, so that any concerns that were found with the external tank could be addressed before they found them on re-entry. Now, sometimes they mounted cameras on the external solid rocket boosters, and these were designed to be recovered. So the cameras could provide a viewpoint looking at the external tank or from below the heat shield of the orbiter. And I think the first time we got this was on STS-93. And yes, that is the same STS-93 with the gold bullet and the Yikes event. They had an 8mm video camera in the forward skirt of each solid rocket booster. So that's the fairing at the top of the booster, above the end of the booster section, but below the nose cone. And this pointed directly sideways at the external tank. And it recorded to 8mm videotape, and they would recover it and then process this after flight. And what they were doing was they were looking for a history of damage to the external tank and the heat shield of the orbiter. So this flew at least a few other flights. But I've not actually seen any video from this ever released, only the odd image. And most of the images are actually in NASA reports, which have been reproduced as blotchy black and white images in photocopies. There's one low-resolution color image from the STS-114 return to flight press kit. But yeah, there are amazing reports with tables summarizing just how many divots appeared in the foam of that external tank thanks to this camera. But in the 21st century, we did finally get some awesome launch footage from the Space Shuttle for STS-112, which added the latest cool thing in rocket technology, Rocket Cam, trademark. This is a commercial product developed in the 1990s, and it initially flew on the Delta II. This was the first time we got to experience the view from a rocket, looking down from the top backwards as it ascended into the sky, and it was marvelous to behold. People complain when rockets don't carry cameras these days. It was expected, but in 1997, it was a veritable innovation. It was amazing to see this. So yes, Rocket Cam, trademark, was developed by Ecliptic Industries, and they sold the camera and supporting hardware as a complete unit for the rocket builders to integrate. The video feed would be transmitted to the ground in real time as an analog TV signal, which means sometimes we get like static style interference when the rocket is adjusting its attitude. Now, looking at the documentation from the era, I don't actually see Ecliptic Enterprises specifying what camera they're using, but NASA later talks about them using it on the Space Shuttle, and they explain that it's a Sony XC999 video camera. And this is a compact CCD-based video camera, which is 12 centimeters long and 2.5 centimeters across. And it's sometimes referred to as a lipstick camera because I guess it was about the size of a big lipstick tube. So this produced like 30 hertz video at 768 by 494 pixels. But then the onboard data handling unit would turn this into interlaced NTSC fields at like 720 by 243, giving a final resolution of 720 by 486. So this same Rocket Cam, trademark, design would fly for over a decade and even move beyond providing launch footage. Dish Network used to have the Earth channel, and it just showed views of the Earth from one of these cameras, which was on a satellite in geostationary orbit. And even further into space, it was used on the L-Cross mission to observe a rocket stage smashing into the moon. And so, STS-112 was the first time that we saw a space shuttle on ascent from a shipboard camera looking down. And this would no doubt have been incredibly useful to observe heat shield damage, say on Columbia's ill-fated mission. But this was a system still in development, and Columbia was STS-107, which means that technically it predated this in the scheduling, even although it launched a couple of launches later. So yes, after the Columbia disaster, they made the external tank camera a permanent fixture on all future shuttle flights. And they also made the booster cameras a permanent fixture. So we have the external tank observation camera, and that's essentially the same system that was flown on STS-93. But now I have technical details. It consisted of an off-the-shelf Super Circuits PC-17 video camera. I think they make like security cameras these days. And it was plugged into a Sony Mini DV tape recorder, and it was positioned again in the forward skirt section of the two boosters, and it looked kind of directly in towards the tank. And it would also give a great view during stage separation or booster separation. So this camera had like a short focal length lens, and it had a 90-degree horizontal field of view. The recording would begin at launch, and it would continue right up as the boosters fell through the atmosphere. And as the drogue parachutes deployed, they would actually switch to another camera that was pointed up so they could actually look at the drogue separation. So that was two cameras on this booster, which gave us some amazing views. But the best part about this was that audio was also being recorded, which allowed you to not only like correlate things that happened in the video with, you know, things that you're hearing, but also we got to hear what it sounded like, which was really pretty special for that moment, actually hearing the sound the boosters make, the engines firing, the little RCS thrusters, the sound of the parachutes deploying. And so a few launches later, STS-16, they finally brought many more angles on the booster. They had cameras that were in the aft section looking upwards, and then they had cameras on the front which were looking downwards. And with the advent of new websites like YouTube, enabling the sharing of video, I remember seeing these angles, and I would do like musical remixes of the shuttle from all these different angles during an ascent. And it's such a shame that by the time this happened, by the time it was so amazingly photogenic, the shuttle's days were definitely numbered. And around the same time, there was a company called SpaceX, and they had started flying their Falcon 1, and every single flight of a Falcon rocket has pretty much had cameras on it. That's why we have video from the very first Falcon 1 flight. I don't honestly know what cameras that SpaceX are using for a lot of these. There's no mention of the rocket cam, trademark, so SpaceX probably rolled their own solution, likely using off-the-shelf parts. And we do know that when fairings were jettisoned and later recovered at sea by people on the ground that posted on Reddit, they had GoPro cameras attached to the interior. And when they returned these GoPros to SpaceX, they shared the footage of the fairings basically falling back to Earth, set to the waltz in the Blue Danube. And it is quite common to adapt GoPros as engineering cameras. There's a lot of knowledge about taking them apart and reusing the guts for other applications. So I suspect a lot of this went on with what SpaceX did over the years. Now, one thing that was likely different is that SpaceX transitioned to digital video. It's not clear if this was there from day one, but the videos seen from the early Falcon 9 launches doesn't show analog static noise like the Space Shuttle external tank video. What we see is artifacts that are much more digital. And by the time they were attempting to land the CRS-3 booster in the ocean in 2014, the data was definitely digital. Because when they first landed the booster successfully in the ocean, they didn't get the data from it because they couldn't get to the booster due to bad weather. So instead of recovering the cameras and getting the data off the memory cards, they only had the low quality downlink data, right? So the data was corrupted, they knew it. SpaceX tried to reconstruct what they could of the footage, and they shared the garbled data stream, which was like in a digital MP4 format. And it was specifically like MPEG-4 part 2, whatever, 15 frames per second or whatever, fixed bitrate NTSC. And so this was posted to their website, and the community at NASA Spaceflight really took to this problem. They created all sorts of innovative methods for guessing at flipped bits and reconstructing more of the video than anyone thought was possible. And the video ended up being featured in SpaceX's famous compilation of footage of how to not land an orbital rocket booster. So digital detective work there, reconstructing a great moment in history. So of course, over time, the cameras did get better, more resolution, better light response, better onboard processing. But the real massive step forward we've seen in the last couple of years has been Starlink, right? Has been able to pull down broadband data from Starship as it launches, orbits, and re-enters. And we see glimpses of the control room, which sometimes show dozens of camera angles being downlinked simultaneously. Many of these are secret, and they show parts of the rocket which, no mere mortal outside of SpaceX is supposed to see. For example, the interior of the propellant tanks. So Starlink has also allowed the first live streaming of re-entry views from the spacecraft. It likely can switch between multiple satellites for the best option, and since it's electronically steered, the Starlink antenna can handle rapid attitude changes in the vehicle, where a mechanical dish may not be able to do that. And so now, before we talk about the landing footage from outside, I do want to talk about other rocket builders. First of all, Rocket Cam trademark is still a thing, and I believe that it's being used by ULA on their Vulcan. I think it's also used on the Atlas V. We actually see press releases about that. So the original rocket camera people are very much still in the game. Rocket Lab, they got some attention when they posted a really cool stage separation video from inside the interstage, and that included audio from rocket exhaust hitting the camera. Yes, there is in fact sound in space, right? And this looked like 360 camera footage at the time because of the way it panned. But later on, we actually got footage from inside the interstage during booster recovery, and you could actually see in there that they had a GoPro Max in there. So I think Rocket Lab is still, as a user of GoPro, still very much alive and kicking in big rockets, although this is a very small big rocket, but you know what I mean, right? So yeah, let's look at that impressive landing footage of the Super Heavy in the Indian Ocean. Not only does SpaceX have cameras watching the launch, but they also had them watching the landing halfway around the world in the middle of nowhere. And according to Elon Musk, the camera they used is in a kiddie pool in the ocean, paired up with a Starlink antenna. And certainly if you look at some of the recovery images from Flight 6, you can see what he's getting at here with the yellow rings, right? More specifically, this kiddie pool is actually a drone which can hold its position based on GPS coordinates. It's a product called Mark Set Bot, and it's supposed to be an autonomous buoy or buoy for boat racing. So SpaceX's support crew basically take one of these things out into the middle of the ocean, and they program it to hold the landing position coordinates, and the bot will just do that, holding its position against the wind and the currents. The camera and support gear is basically sitting on top of this. It's got a battery, solar, Starlink antenna for remote control. It's got a camera or two, and some drones which they launch from this. And presumably they have to operate these from a fair distance away. So they're probably actually operating these over the Starlink network, which is pretty insane to think that they're flying drones from that far away. I mean, it honestly does feel like magic that they're able to fly a drone via a satellite from anywhere in the world to watch a booster come back from space, fly, and soft land in the ocean. And it does make me wonder why there's no cameras on those Starlinks that they launched from space, from that flight. Come on, we've done everything else. We want to see that next. I'm Scott Manley. Fly safe.